Alejandro Montes, and this is my Lab 5 magnetic braking with Faraday's law. Introduction. The purpose of this lab is to observe the magnet falling through the aluminum foil cylinder, compare the real results with the computational model, and understand how Faraday's law explains generation of current. For the physical principles, we have magnetic flux, which is the amount of magnetic field passing through a normal to an area. Faraday's law, which says that voltage is the negative time derivative of magnetic flux. Lenz's law, which states that induced current creates a magnetic field that opposes the flux. For our physics models, we have a falling magnet creates a changing magnetic field at a ring. The cylinder is just an infinite stack of those rings, and d flux dt points downwards. Also, Lenz's law, this will tell us that the magnetic field due to the current must point upwards, and current will flow counterclockwise from above. Magnetic force is equal to I times dl cross b. You find b using the Biot-Savart law, and the magnetic force is derived to be I times 2 pi times r times b times sine theta. For this experiment, the procedure, we wanted to record the physical properties of the cylinder, which include its length, thickness, and inner radius. Then we drop the magnet down the cylinder, north pole first. We measure the time it takes to reach the bottom and average 5 trials. The results preview. The experiment got an average of about 1.7242 seconds, while our computational model came out to be just 0.442 seconds. And why not use a ferrous tube? Iron has a ferrous metal like iron has certain ferromagnetic properties that interfere with Faraday's law. Our measured quantities: the cylinder length is 0.46 meters, the width is 0.005 meters, inner radius is 0.025 meters, and the outer radius comes out to 0.03 meters. The resistivity is 2.65 times 10 to the negative 8th ohm meters. As for the magnet, we have a mass of 0.023 kilograms and a mu value that we calculated from Lab 3 of 2.1 amps per meter squared. Then we have our observations. We did 5 trials. Each of the recorded times for each trial is shown there, as well as the average. What happens to the magnet? And how does this compare to free space without a tube? Well, in this experiment, we find that the magnet kind of floats, meaning that it falls slower than it would in free space, and therefore we know that the downward force must be of lower magnitude than in free space, so the cylinder applies some sort of upward force on the falling magnet. Jumping into the code, this just shows how I modeled the cylinder. I created a cylinder and modeled it using a for loop. And then the magnet, we just input the mass and the mu mag that we had from before and modeled the magnet. To get the B field and d flux dt. To get the B field, we used Biot-Savart law, and we created a function to get this. It's shown on the screen. It's essentially using that B dipole formula. And then just to calculate the flux, the d flux dt, we have this function here, which takes the radius of the ring, the distance, the speed of the magnet, and throws them all into this equation that calculates df dt. In the end, it returns this plot of velocity over time versus time, and as you can see, the time in the tube in seconds comes out to be 0.442 seconds. And this is different than the actual results. This is because conditions are not perfect, and there will obviously be some drag, as well as potentially some errors with timing it. As for the reflection questions, what if the resistivity of the conductor were reduced to as close to 0 as possible? How would this change the dynamics of the falling magnet? Well, current and resistance are inversely proportional, therefore current would grow in magnitude, and the magnetic force would grow in magnitude, and the magnet would then fall more slowly. Conversely, if we had holes or slots cut into the tube, it would affect the ring currents in our model because the cylinder would contain less hole rings overall. Therefore, there'd be a weaker magnetic force on the magnet, and the magnet would fall faster. All right, thank you for watching.